Hi everyone, I'm going to do problem 39 right here. We'll see if I can do the other problem as well. I'm going to try and see if I can do it. But first I want to try this little pre-problem I have here. We have some person over here. They're hanging from a spring scale, and then here they're standing on your typical bathroom scale. And we are going to find out what the spring scale and the bathroom scale would read. And I'm going to start with the spring scale. The person has a mass of 62 kilograms, by the way. So in order to find this out, I'm going to make the person our object. So the person, we make a dot, and then I'm going to draw a free body diagram of the forces acting on the person. So let's see, there's going to be the weight, mg, pulling down on the person. That's the earth pulling down on the person. But then there's also going to be the force from the spring scale keeping the person up, and that's going to be, I'm going to call that Fs, the spring force, the spring scale force. So, okay, now I can, and then the person we're saying is at rest, so the velocity is 0, and then the acceleration is going to be 0 as well, so we're going to keep this pretty simple. So if that's the case, I can then go to Newton's second law, F net equals ma, and my net force is just the spring force pulling up and the weight pulling down. So that's going to be the spring force. Let's make that a different color so it doesn't screw anything up. Spring force minus mg equals the mass times the acceleration. But in this case, my acceleration is 0, as we said over here. So this is all just going to be 0. And that's going to leave me with the spring force equals mg. Well, I know what the mass is. It's just 62 kilograms, so I can just plug this in. It's going to be the spring force equals 62 times g, which I'm going to approximate as 10 newtons per kilogram. So that's going to be the spring force equals 620 newtons. That means I'm going to get a reading around here of about, we'll say it says, 620 newtons. So let's just say that that's what that reads. So what would it look like then for the person on the bathroom scale? Well, it's going to be exactly the same thing, except now the bathroom scale is this force we're calling, I'm going to call the normal force, because there's a normal force from the bathroom scale acting up on the person here, and then there's also the person's weight coming down here. If you can see, and then also the velocity is 0 and the acceleration is 0. So all these initial conditions are the same. If you can see, it's exactly the same free body diagram, but instead of the spring force, we got the normal force. So I'm going to get exactly the same information with Newton's second law, except this is going to be a normal force, and that's the force that the spring scale would, or that the bathroom scale would read. Just like the spring force here is the force that the spring scale would read. So this is also going to be 620 newtons. So that's my pre-problem right there. And let's go now over here. The big question here is, okay, this is given these initial conditions, that the initial velocity is 0 and the acceleration is 0. But what would happen if I actually have an acceleration, and in this case, there's a downward acceleration of 3.8 meters per second squared, and what would happen in that case? How do things change? So let's just read this really quickly. It says a student's backpack full of textbooks is hung from a spring scale attached to the ceiling of an elevator when the elevator is accelerating downward at 3.8 meters per second squared. So it's accelerating downward at 3.8 meters per second squared. The scale reads 60 newtons. So I got the scale reading 60 newtons right here, my acceleration pointing down. What is the mass of the backpack? So now we're going to try to find the mass of the backpack. I am again going to start with a free body diagram. So this is part A. I'm going to start with my free body diagram. I'm going to make the backpack my object. So the backpack is my object. That's what's going to be drawn here. So I'm going to get a force from the spring scale pointing up, and I'm also going to get a weight pulling down. And I've drawn the weight as being bigger than the spring force, and that's because I have an acceleration in the downward direction. So I know, given that there's only two forces, this one has to be the bigger force. Okay, now I can go into the second law. That's going to be F net equals ma. My net force is just the spring force pulling up minus mg pulling down equals, I do have an acceleration this time, so it's going to be the mass times the acceleration. And now I'm trying to get the mass So I'm going to isolate the mass. First thing I'm going to do is add mg to both sides. Then I'm going to have the spring force equals ma plus mg. And I can see I got mass in both these terms here, so I'm going to factor out that mass, and then I'll get m times a plus g equals the spring force. So last thing I'm going to do is I'm going to isolate m by dividing both sides by ag, a plus g. And that'll give me that the spring force over a plus g equals the mass. The spring force, they told me, is a reading of 60 newtons. So that's just going to be 60 divided by the acceleration they told me was 3.8 meters per second squared, but it was down 3.8 meters per second squared. That means it's going to be negative 3.8 plus g. They're giving me 3.8, so probably 9.8 is going to be the easier thing to use here. You're free to use 10. That would work as well. But I could see this is just going to be 60 divided by 6 equals the mass. And that's going to give me 10, I hope, kilograms. So 10 kilograms right there is going to be my mass. All right, there we go. So that's the mass of the backpack right there. So next up they say, what does the spring scale read if the elevator moves upward, speeding up at a rate of 3.8 meters per second squared? Again, that's an acceleration, except now it's accelerating upward at the same rate, 3.8 meters per second squared. Okay, what does that look like? So again, I can draw my free body diagram. The free body diagram really doesn't change. The only thing that's going to change is that the spring force is now going to be bigger than the weight, because I'm accelerating upward at 3.8 meters per second squared. My Newton's second law isn't really going to be all that different. F net equals ma. That's going to give me the spring force minus mg equals the mass times the acceleration. And we're trying to get the spring force, right? What does the scale read? So what does the scale read? So I'm trying to solve for Fs. So if that's the case, I'm just going to add mg to both sides. That's going to give me Fs equals ma plus mg. Again, I can make this a little easier on myself when I do the calculation by adding, factoring out the m. So it's going to be a plus g. And this is going to make it a little easier for me. So I got the acceleration. So it's going to be 10 times the acceleration, which is positive 3.8 now, because it's accelerating in the upward direction, times g, which is, I don't want to switch it in the same problem, right? Fine. 9.8. I'm going to break out the calculator because I don't want to think about this. 9.8 plus 3.8 times 10, that's just going to be 136. So I'm getting a spring force of about 136. You could approximate to 140 if you'd like, newtons, and there we go. All right, next up, now they're saying for C, what does the scale read if the elevator moves at a constant velocity? Well, what is my acceleration at a constant velocity? 0. So my acceleration is going to be 0 in this case. Well, if you can realize, a lot of these free body diagrams are the same, but what the hey, I'll do it again. So in this case, I got an acceleration of 0. So if it's 0, that means that the spring force is going to be exactly equal to the weight. So again, I can apply this to the second law. F net equals ma. Again, this is going to be the spring force minus mg is equal to, except the acceleration is 0. So if the acceleration is 0, 0 times anything is going to be 0, and that's going to give me 0. So in this case now, the spring force is just going to equal the mass times the gravitational field, or the spring force is going to equal the mass, which is 10, Gravitational field is 9.8 newtons per kilogram. So my spring force in this case is going to be 98 newtons. Last question, part D. Says, if the elevator had no brakes and the cable supporting it were to break loose so that the elevator could fall freely, what would the spring scale read? So all elevators have emergency brakes so that they don't do this, but we're saying, okay, let's say that this happens. So basically the elevator is falling freely. What would the spring scale read? So if the elevator is falling freely, here's the spring scale, here's the backpack. If the elevator is falling freely, that means its acceleration is equal to negative g. And so if its acceleration is negative g, well, these things are also going to be falling freely, both the spring scale and the backpack. Everything is going to be falling at the same rate, negative g. So that means that, so that means that if this is falling at negative g and this is falling at negative g, we have only the gravitational force acting on the backpack and the spring scale. Both of them are falling. In that case, then, the spring scale is not going to be holding up the backpack anymore. It's not going to be exerting this force, keeping the backpack where it is. They're both going to be falling, and in that case, they're both going to be falling downward like that. And so the backpack's only going to feel a force mg. There is no spring scale force holding it up now anymore. And if that's the case, then the spring scale force is going to equal 0. So there you go. And I'm going to try and see if I can do the trapeze artist one as well. That might be coming up later in the day, though. So, all right. Cool. All right. There you are. See you guys Monday for dropping eggs. That'll be fun. All right. Bye.